Hello everyone, here we'll be talking about cross products, and the main definition for cross product is that if we have two vectors A and B labeled as such, then the cross product is given by this crazy thing, which I know is a lot to look at. And the main motivation for cross product is that it's actually a vector that is perpendicular to both A and B. So if you imagine A and B being some vectors in three-dimensional space, something like this, and you imagine the plane that they both lie on, then the cross product is some vector that is perpendicular to these two vectors, to each of them. So perpendicular to B and simultaneously perpendicular to A. So I'm trying to draw it kind of like that, if you can see that. Now, why this comes about is basically if you solve that type of equation. So if you call this vector C, for instance, and notice if two vectors are orthogonal or perpendicular, then their dot product is 0. So if you let A dot C be 0 and B dot C be 0, and you solve for C, which is C1, C2, C3, one solution is this solution, and we just call that the definition for cross product. So that's the main motivation behind cross product and why this definition kind of holds. Now, one thing that I mainly want to kind of talk about is what these kind of remind me of, and it gets a little funny because it gets more into a linear algebra type deal, and if you don't know what that is, linear algebra is a class that is essentially algebra of matrices, and what this reminds me of are determinants. So let's recall determinants for a second. And first I'll show you determinants of 2 by 2, and then we'll talk about 3 by 3. And the cross product mainly pertains to three dimension vectors. So that's what we're going to be taking a look at. So if we want to take the determinant of a matrix that's a 2 by 2, so let's say it's A, B, C, D, then this determinant is equal to AD minus BC. So it's kind of like this cross multiplication. This times this minus this times this. And notice these vertical lines here mean determinant up. And there are other notations for that, but the straight line notations would all be using. So this is really the determinant of the matrix whose entries are A, B, C, D. And very similarly, we can actually write the one for, so this for 2 by 2s. And then we can write very similarly the one for 3 by 3s. There's actually a few ways of writing determinant for 3 by 3s. In fact, I don't think we really need it, but I'll just show you. So if you have a 3 by 3, A, B, C, D, E, F, G, H, I guess. Then this determinant can be written in a few ways, but one way that we like to do it generally is we'll use, I guess we can use this column. We can use rows or columns. And in fact, what I'm noticing is that I think the book, so it's a little funny, but the book is using A, B, C, D here, but for 3 by 3s they're using a different notation. But I'm just going to stick with this one, even though it looks a little different, but that's fine. So I'm going to actually go by, since it's A, B, C, I'll go by rows. So if I use this row, then I'm going to use each of these letters, A, B, and C, multiplied by these determinants of 2 by 2s that you get by kind of crossing out the row and column that contains that letter A, B, or C, which I know sounds kind of funny. And not only that, we'll alternate the signs, plus, minus, plus. Now this, believe it or not, basically is kind of the definition of a determinant of higher dimension matrices that are not 2 by 2s. There's a shortcut you can use as well that I'll probably talk about in a little bit. But if you cross out the column and row that contain A, you get only E, F, H, I. So let me write it like that. And similarly for B, you get D, F, G, H, or D, F, G, I should say. And for C, if you cross out the column and row that contain C, that is D, E, G, H. D, E, G, H, sorry about that. There we go. And if you were to use the definition of 2 by 2s, you can actually get something a little different. I don't know if I should actually write that out. Yeah, it'll be too much if I actually write that out, but you can try that on your own, and notice all I'm saying is that if you use the fact that this determinant is this times this minus that times that, and this one times that minus that times that, and similarly you'll see a similar pattern there. you can actually write it out and distribute these A, B, C's. But what that kind of gives in general, there's a rearrangement of that. It gives what is called the Rule of Soros, which I'm not going to risk writing because I don't know how to spell his name. But this is kind of like, let me just call this a shortcut for 3x3s. Which again, I don't think we really need. But the shortcut is doing the following. It's writing the matrix, the 3x3 matrix, A, B, C, D, E, F, G, H, I, and repeating the first two columns, A, D, G, B, E, H, and then multiplying like this. A times E times I, B times F times G, C times D times H, minus the other way around. So we're doing this one minus G times E times C, F times H times A, and then I times D times B. So it's these added minus these added. So it's actually literally this idea here for 2x2s, that minus that, only now we have this kind of 3 scratch minus that 3 scratch, which I think is a kind of more practical maybe. But I may show examples of these if we need them. I don't think we'll actually need them entirely, but 2x2s we'll definitely need. So now I'm going to show how this relates to this. In fact, I didn't do any examples, but let's just do a small example here, just to kind of show you. So we want to take the determinant of 2, 3, negative 5, 4. It is just 2 times 4, which is 8, minus 3 times negative 5, which is negative 15. And notice it's a double negative, so it's positive, so the determinant here is actually 23. Perfect. So now what we're going to do is I'm going to erase this and try to give us some interpretation of cross products involving determinants. All right, so I've erased our recall of determinants but left everything else. And I wanted to point out a few things. And mainly what I wanted to remind us of are the basis unit vectors I, J, and K, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. They're vectors, of course. And I wanted to emphasize that this component, and this component can actually be written as the coefficients of I, J, and K if we write this in I, J, K form. So this would be the coefficient for the vector I, for the vector J, and for the vector K. And if you take a look at what's multiplied to I, for instance, it's A2B3 minus A3B2, and this looks very much like what we saw for a 2x2 determinant. In fact, if we were to write this as the determinant of a 2x2, it would be this diagonal, so A2 times B3, and I'm going to keep the A's on top, so minus this diagonal, which is A3 times B2, okay? And notice that's multiplied by I. So that'll be multiplied by I. In fact, one way we can write this out, I don't think I want to do it completely, but I'll do it a little bit actually. So let's write this. Let's write the cross product A and B as the following. The determinant of A2, A3, B2, B3 times the vector I. Looks kind of funny because we have a dot then a hat, but that's okay. And then we have minus now, and you'll see why it's minus in a second, but I want A1, A3, and B1, B3. So I'm trying to keep things in order as far as subscripts go, and I'm trying to keep the A's on top and B's on the bottom. So notice this would be A1, B3 minus A3, B1, but since this is the other way around, we need a minus here. And now I think things are kind of shaping up to be a little more obvious, that this is starting to look kind of like what I saw and what I gave you for when we recalled the determinant of a 3x3. So that actually does kind of come up a little bit in this. And now this would be plus the determinant of, it's going to be A1, A2, B1, B2, K. So maybe you can see exactly what this is. Basically what we're saying is that this cross product, the way it's defined, is really just the determinant of the 3x3 whose top row is just the vectors I, J, K, and whose bottom two rows each are the vectors A and B. Nice. So all we really need to do to find the cross product of two vectors A and B is write them as the bottom two rows of a 3x3, where the top row are the unit basis vectors I, J, and K, and then take the determinant of that 3x3. And that's really it. So that's the big motivation, well, not motivation, but that's kind of the big relationship, I guess I could say, between our definition of cross product and determinants and the vectors I, j, k. So now we're going to move on to something a little different. In fact, we'll do an example of this first, where we actually take the cross product of two vectors. So let's take a look at that example right now. All right, so for this next example, we want to take the cross product of these two vectors, and then this theorem that I stated after basically just says that the cross product of two vectors is orthogonal to each of the vectors. And this was kind of from the definition. This is the motivation for the definition, really. So the fact that this is a theorem is based on the definition, but the definition comes from the motivation to aim towards this. So this kind of goes without saying. I'll attempt to prove a part of this at least, though, just to kind of feel complete about it. But let's first take a look at this, of course. Now remember that to find the cross product of these two, this is just going to be equal to the determinant of the 3x3 whose entries are the vectors I, j, k, and whose bottom two rows are 1, 3, 4, and 2, 7, negative 5, like that. Remember, order kind of matters here. It's unobvious yet if cross product is commutative. In fact, you can try to prove that to yourself if that is indeed the case by swapping these two and seeing if you get the same result. But I'll leave that for later discussion after we finish talking about this. In fact, we'll talk about some properties of cross products later on in the video. But for right now, let's see. So we want to take the determinant of this 3x3, and notice if we cover the column for I and j, column and row for I and j, we get the determinant of 3, 4, 7, negative 5 times the vector I minus the determinant of 1, 4, 2, again, 1, 4, 2, negative 5 times the vector j. So I hope you see how you did that. You cover the column and row that contains j, and you're left with, there we go, 1, 4, 2, negative 5. Hope we can see how there we go, looks good. Anyways. And then plus the determinant of the 2x2 when you cover the column and row that contain k, that's 1, 3, 2, 7 times the vector k. So let's see what we end up getting here. The determinants of these, remember, is just the crisscross determinant. So it's negative 15 minus 28, that's all times I, minus, this is going to be negative 5 minus 8, that's 4 times 2 after all, times the vector j, and then plus 7 minus 6, that's pretty easy to compute, that's just 1, times k. So all in all, we get negative 43, looks like I, and that's going to be negative 13, but with the extra negative out here, we get positive 13 j, and then plus 1 times k. So in reality, if you wrote this in component form, it would be the vector whose components are negative 43, 13, and 1, respectively. Nice. Now, there is no way I'm going to even attempt and try to do this, but if you were to actually write out these vectors, or draw these vectors, or sketch these vectors in 3-space, and this one as well, you would actually see that this vector is indeed perpendicular to each of these. So that's kind of nice. Now, notice from the definition, this is just a vector. It's not the single distinct vector that's perpendicular. In fact, there are infinitely many, if you think about it. There's a bunch that face up and a bunch that face down. In fact, you can take any scalar multiple of this vector, and it'll still have the same direction, which will be perpendicular to these two. And in fact, a nice visualization that I think helps and kind of leads into the next idea after discussing this theorem is that if we have these two vectors in three-dimensional space, A and B, and you can consider this kind of angle as you sweep from A to B, so the angle between them, in other words, let's call it theta, then what you end up getting is this vector that goes up, and this will be the vector A cross B. So this is, again, perpendicular to A and also perpendicular to B. And in fact, what this kind of reminds me of is the right thumb rule. So notice the curling of your fingers corresponds to going from A to B, and the thumb represents A cross B. So in fact, it's true that B cross A would not necessarily give you the same thing. In fact, they are basically going to be negatives. But I'll allow you to kind of figure that out on your own. And again, we'll write properties that'll kind of show that and more. But for right now, let's talk a little bit about this theorem. I there's no way I'm going to have time to prove all of this, but I'll prove it a little bit. So A cross B, I want to say that's orthogonal to A and then to B. But I'm just going to show that it's orthogonal to A. So to prove this, I'm going to take so this is for A only. And the way I'm going to do this is basically just take the dot product of A cross B, that's a vector, and the vector A. Now notice that this vector is going to be the vector whose components are the determinants of these 2x2s, which the order kind of escapes me right now, but I guess I can write it out here because I don't have too much space here. So A cross B is going to be, this is how I remember the ordering. So it's AB minus AB minus, well, comma AB minus AB, comma AB minus AB. And here's how I remember it. The first one doesn't include 1, so it's 2, 3, 3, 2. The second one doesn't include 2's, so it's going to be not 1, 3, but it's the opposite order that you'd expect. So it's 3, 1, 1, 3. And the way I remember that is because of the determinants, the alternations in the middle, so it's plus, minus, plus, like that. So similarly here, this one doesn't contain 3's in the subscript, so it's going to be 1, 2, and that is in order, because again, the plus, minus, plus. And we're dotting that with the vector A, which is A1, A2, A3. Perfect. Now, when you take the dot product of these, what you end up getting is, let's see, it's going to be A times each of these, well, A times this one, A1 times this one, so it's A1, A2, A1, A2, B3, minus A1, A3, B2, plus A2 times these, so it's going to be A2, A3, B1, plus A2, A1, B3, okay, and then A3 times this one, so it's going to be A1, A3, B2, I guess I'll keep it in order, so let's just do A3, A1. I hope it's not looking too confusing, maybe you can kind of see the idea so far. And a very similar thing happens when you take the dot product of B. So notice that all of these actually cancel out and we indeed get 0. So A1, A2, B3 actually cancels out with, did I miss a sign? I think I did miss a sign, didn't I? This should have been a negative. So this actually cancels straight up with this one. This one, A1, A3, B2, cancels with this A1, A3, B2. So the negative, positive. And this A2, A3, B1 cancels with this A3, A2, B1. So they end up being the same because multiplication is commutative, basically. So we indeed get that it's 0. So since it's 0, the dot product of these two are 0, that means they're orthogonal indeed. Now again, that's only showing it for A. If I were to show it for B, it would just take too long. But it's the same exact idea, just with B1, B2, B3 instead. And you get the same, well, similar cancellation anyways. So now let's take a look at an idea that has to do with this angle business. And it'll be pretty similar to what we saw from the previous section with dot products. So let's see what that's all about right now. Right, so now this theorem says if theta is the angle between vectors A and B, where theta is in between 0 and pi, which I'll discuss a little bit in a moment, then the following holds. The magnitude of the cross product of A and B is the product of the magnitudes of A and B times sine of the angle between. So now getting to this whole being in between 0 and pi part, imagine if you have two vectors in three-dimensional space, A and B. When I ask you to find the angle between them, what comes to mind? Not this angle, but instead maybe this angle. So for whatever reason, it's kind of like a language thing. When we say angle between, we always kind of focus on the angle in between them that is less than 180. So in fact, this by definition kind of the word between really just gives us that it must be in between 0 and pi. So that part I think is pretty safe to say. Now, as far as why this holds, well, maybe first you may think this looks pretty similar to a result we saw from dot products. Notice that A dot B is equal to the product of the magnitudes A and B times cosine of the angle between, where cross products have to do with sine, not cosine like dot products do. So there's a lot of parallels we can kind of relate. In fact, we'll see one in a little bit after we prove this. Speaking of which, to prove this, I kind of feel bad about something. So let me just kind of get into the proof a little bit, and then I'll kind of explain what I feel bad about. So I'm going to prove this. I'm going to try to prove this. And I'm going to leave a little detail out because it's just too much to write on the board and the video will be too long. But it's not something that's terribly long for you to verify on your own. And that is that if you take the square of the magnitude of AB, remember that the magnitude of a vector is the square root of the sum of the squares of its components. So when you're squaring the magnitude, the square root part goes away. So this is literally just equal to the sum of the squares of its components. And if you remember what the components are, we've established already a lot in this video so far. That was the whole A2B3 minus A3B2 thing, where that's the first component and the second, third, and so on. And remember, that's really just the determinant of that 3 by 3 that we've been kind of working with, especially from the last example. So you can actually expand it out as being the first component squared plus the second component squared plus the third component squared. Then you can expand that out. And then you can also expand this out, the magnitude of A squared times the magnitude of B squared minus the dot product of AB squared. So I'll allow you to verify that on your own, that is indeed true. And yeah, so that's all I'm going to say right now. But I'll allow you to verify that on your own. But the only really way of seeing it is by kind of expanding each of them out and seeing that they end up being the same. Now notice that this is going to be A1 squared plus A2 squared plus A3 squared. That's going to be the same thing, but with B's instead of A's. When you multiply those out, you have to expand it to kind of see what that gives. And then here, this is the dot product of A and B, which would be A1B1 plus A2B2 plus A3B3, all squared, so expand that out. Combine terms, and you'll see that the terms combined here are exactly equal to this mess. So now that I have that, so that's the part I kind of felt bad about, and I'm missing this vector notation for a lot of these. Again, I just feel bad not showing that they're this equality holds, but allow you to expand that on your own. Now from here, we can actually say a lot. So the dot product between A and B is just what? So here this is straight up multiplication because these are just magnitude squared. Even though I'm using kind of the same symbol. This is multiplication, where this is an actual dot product. So I hope that part's not confusing. And now notice dot product from what we saw previously that I kind of mentioned just now, is that this is the product of the magnitudes of A and B multiplied by cosine of the angle in between. And that whole thing's squared, so we can just square each part of the product like that. So magnitude of A squared, magnitude of B squared, and cosine squared. And notice these are actually the same. So if we factor out the magnitudes multiplied together squared, we get this is the magnitude of A squared times the magnitude of B squared, all multiplied by 1 minus cosine squared. And notice there's a Pythagorean identity for trig functions that says 1 minus cosine squared is actually equal to sine squared, because sine squared plus cosine squared for all angles, as long as they're the same angle, of course, is equal to 1. And that actually does it, because then we can square root both sides, and then we can finally get this equality. So I'm just going to end it there. I've left out a little bit of detail, but I think you can fill in the blanks on your own. I don't think that's too terrible. Now this corollary is kind of interesting. So this basically says two non-zero vectors A and B are parallel if and only if their cross product is the zero vector. Now again, it's a corollary, meaning that follows from this theorem. So of course you can kind of see it. It has to do with this guy being zero. So I'll kind of prove this a little bit. So I'll say two non-zero vectors A and B are parallel quotations, if and only if, well, the angle in between them is either 0 or pi. Okay. Now, why that's true is because even if the two vectors are the same, remember that a vector can float around anywhere in the space it lives in. So let's imagine it's a three-dimensional vector. So let's say A and B. So if they're parallel, it means they have the same direction, but possibly different magnitudes. Now, in fact, they don't really have the same direction. One can go one way and one can go the other way. And that would be if their angle between would be pi. So here, if you kind of pile them on top of each other, so float A over B, their angle in between is actually 0. So imagine these kind of collapsing. Whereas if it was facing the opposite way like this, then if you were to connect them tail to tail, you see that the angle between them is actually pi. So that's why this kind of holds. And in fact, since sine of 0 and sine of pi are both equal to 0, then this equality collapses to the dot product being, well, not dot product, but the cross product having magnitude 0. So this implies that the magnitude of the cross product is equal to the number 0, which implies that the cross product itself must be the 0 vector. Because the only vector that has a magnitude of 0 is the 0 vector itself. And in fact, all of these statements are actually if and only if. So that completes the proof there. So I hope that part was okay. That, I think, is not too hard to handle. But this first proof is definitely a little intense, especially if you prove this fact on your own. All right. So now we'll take a look at something a little different. In fact, I'm basically going to write on a list of properties of cross product that we've seen so far. Kind of. So let's take a look at that right now. All right, so here are the list of properties that I was just discussing, as well as some pretty useful facts. These are pretty useful. This is not really in particularly useful, but it's a fun fact, I guess you can say, of cross products. Now let's go in order here. So let's discuss these properties. Now I'm not going to prove each of them, but I'll discuss a little bit and kind of give you an idea of why they're true. Now this one we kind of talked about a little bit today. If you take the cross product in opposite order, you do not necessarily get the same result. You get negative of the result you would have gotten otherwise. And we kind of explained this by that right-hand rule, that if you go from A to B, then the perpendicular vector to each of A and B is the cross product. So if you would go to A from B to A, then you would have the one that's negative that. So that visualization makes sense. But if you actually work through this yourself, where A is A1, A2, A3, and B is B1, B2, B3, then you can actually convince yourself that's indeed the case just by doing it out. In fact, all of these properties can be shown just by basically relating each side of the equalities using those expansions of A and B, and I guess C in some of these cases, and you can verify that they're indeed true. 2 is pretty interesting. It says if C is a scalar, then we kind of have this passing through of the scalar. So C can be scaled to A or to the whole cross product or just to B itself. So C can kind of pass in and out of each part of the cross product. 3 says that cross product over addition distributes. So A cross B plus C can be written as A cross B plus A cross C, or here C is not a scalar but a vector, so keep in mind the arrow hat on top has great significance here. Property 4 says the exact opposite, kind of. It says that distribution works in the opposite way as well. But you have to make sure that the orders are correct. And in fact, this is really easy to show given that we know 1 and 3. Because if you were trying this the other way around and swap them, using property 1, you get a negative that result. But then if you distribute C using property 3, then you get negative of each of them because the negative distributes. And then you can negate each of those by swapping them back using property 1 again. So that's kind of interesting if you want to try that on your own. But 1 and 3 I think are pretty useful to prove on your own. 1, 2, and 3 really are. Property 5, this is actually kind of special. This is known as a triple scalar product. And the triple scalar product will actually come back a little bit in, I'm sorry, it's scalar, I was just checking the wording. It's scalar triple product. So let me point to that. The first part here is called the scalar triple product. Scalar triple product. Now the reason why it's called scalar is because it actually is not a vector itself, it is a scalar. And how do I know that is because A cross B is a vector, and a vector dotted with a vector is a scalar itself. So that makes sense. And it says that this is true. If you take the dot product of the cross product of two vectors, it's the same as taking the cross product of the first two dotted with the second one. So that's a little interesting, and I would like to prove that, but it's a little involved, and it's similar to kind of proving the previous proof we went over involving sine of theta. It's a little long and it requires expanding out. So it's not difficult to do, you can try it on your own. 6 is kind of interesting. It says if you have the cross product of A and the cross product of two other vectors B and C, then this weird thing holds. Where notice that A dot C and similarly A dot B are each scalars, and then multiplied to these vectors, or scaled to these vectors B and C, subtracting those results in this. which I think is kind of wild, and that requires a proof on its own, I think. But again, anytime cross products are involved in a property and you want to prove a property involving said cross products, it's a little involved because the cross product is that crazy expansion of the determinant of that 3x3 we saw, so it's a little hard to show that. But again, you can verify each of these on your own. It just takes a little bit of time, and I would love to do it, but the video would just be too long, which I know sounds like an excuse, but it's not. And now for these facts, I'll kind of again discuss each of these in order. So the first one says that the length of the cross product, magnitude of the cross product of A and B, is the area of the parallelogram determined by A and B. And this is actually not too hard to show. So imagine we have these two vectors A and B floating around in three-dimensional space, but just for simplicity, imagine it's plastered on the board here. And we have the angle in between them, theta. Now if we were to create a parallelogram by looking at B and floating it over here, and copying A over and floating that over there, which remember you can do with vectors, then you get this parallelogram. Now the area of a parallelogram, if you don't know from geometry, is just the base times the height. Now the base here will have length, magnitude of B. And the height, using trigonometry, is actually going to be, well, it involves sine, because this length is the magnitude of A, and sine of this angle is opposite over hypotenuse, so that means this must have to be, well, this must be, let me do it like this, I guess. This has to be the magnitude of A times sine of the angle. And notice, if you do base times height to find the area, you just get the magnitude of A times the magnitude of B times sine of the angle, and that exactly is the magnitude of A cross B, just like we showed in the previous screen. These next facts are kind of interesting. It says I cross J is K, J cross K is I, and K cross I is J. Now, I'm not going to prove these necessarily, but it's not too hard to verify whether it's true. It just kind of, well, in fact, maybe I'll just do one of them. So let's look at the first one. So let's take the cross product of I and J. So remember how that goes. You want to take the 3x3 determinant for ijk, and then I, which is 1, 0, 0, j, which is 0, 1, 0, and then taking the determinant of this, it's going to be the vector. Moving the I column and I row, we get I times the determinant of this, which is 0 times 0 minus 0 times 1, so that's just 0 for the first one. So you kind of see if 0 is involved, then it just becomes, in each diagonal that is, it becomes 0 itself. For the j one, if you remove j and the j row and j column, you get 1 times 0, 0 times 0, so that's also 0. And then finally for k, if you remove the k row and k column, you get 1 times 1 minus 0 times 0, and that's 1. And notice this is exactly k. So notice the order, alphabetical order, kind of works in your favor. So we have ij gives you k, jk gives you I, but ki gives you j, and that's not in alphabetical order. So what do I mean by this? I mean that if you write these in order, I, j, k, in alphabetical order, and you go from left to right, I times j will give you the other one, or I cross j will give you the other one, k. So that's ij, that gives you k. If you look at j and k, let me use arrows, I guess. So I and j cross to give you k. J and k cross to give you I. Because not only are they in the same order, but they're actually consecutive letters, is one way to think of it. But notice, I and k are not consecutive. So if you take their cross product, I cross k, that'll actually give you negative j. So the cross product in the opposite order, k cross I, will give you j. So that's one, this is not the reasoning why that's true, but it's a nice way of remembering that. So that's the last thing I want to say in this screen here. So now we'll move on and we'll discuss something else. In fact, we'll take a look at a result that kind of has to do with the scalar triple product, and then we'll see an example that will involve these properties. Right, so here this definition was what I discussed previously, the scalar triple product, just a little more formally here. The scalar triple product of the vectors A, B, and C is this. It's the dot product of A and the cross product of two vectors B and C. And we had that property 5 from the previous screen that holds. Now, one really fun fact, very similar to what we just discussed with the cross product having magnitude equal to the parallelogram area, we have this volume of this so-called parallelepiped, which is kind of like a three-dimensional parallelogram, and I'll draw one shortly, determined by the vectors a, b, and c. The volume of that is the magnitude of the scalar triple product. Now, I kind of hesitate to say magnitude, because here, notice that the cross product is a vector, and then the vector dotted with the vector is just going to be a scalar. So here, this does not mean magnitude, this legitimately means absolute value. Now I'll describe why it's true a little bit, but first let's kind of get an image. So let's imagine we have these two vectors, let's use B and C as our kind of floor vectors. Now, the way I'm drawing it's going to look a little funny, but basically I want B and C to be these vectors in 3 dimensions, and I'm going to flatten them as to be our floor. And then we'll have some vector A coming up like this, that'll be kind of like this vector sticking up. So I'm going to attempt to complete this so-called parallelepiped by just extending the floor with C and B like that, and then extending A upwards like this in this third dimension. Now if you extend B like that, we kind of extend a little more, and then C like this, B like that, you kind of see what I'm going for, but my arrows are just aren't long enough. But there we go. So we end up getting this, which looks kind of like this skewed box, and basically it's a 3-dimensional parallelogram. Because parallelogram we think of like as a skewed box in 2 dimensions, parallelepiped would be a skewed box in 3 dimensions. Now I'm going to try to explain a little bit why this is true. Basically, the area of this floor parallelogram is just the cross product of B and C. So that part isn't too hard to verify. At the same time, we have the cross product actually being this vector, cross product of B and C that is perpendicular to both the vectors B and C. And then this angle in between these two, let's call it theta, between the vectors A and BC, we can actually find the height of this parallelogram. We can call it h, let's say. But using trigonometry, it ends up being the case that h is actually equal to the magnitude of A multiplied by cosine of the angle. Kind of similar to how we saw for proving that the area of the parallelogram was the magnitude of the cross product of two vectors. So it's very similar argument. And now all we need is from geometry, the area of such an image here is actually, not area, but the volume of such a parallelepiped is just going to be the base area multiplied by the height h. So really what we're kind of saying is that this volume then is just the base area times the height h. But since the base area is the cross product, the magnitude of the cross product of B and C, which is this part, and since h is the magnitude of A times cosine of the angle, then what we end up getting is, I don't really have too much space here. I guess I'll write it out over here. Hope you can see that. But I'll write it here. So far we have magnitude is the base area, which is the magnitude of the cross product of B and C, and the height is the magnitude of A times cosine of the angle. But what do we know? We know that if we have the magnitude of two vectors multiplied together, multiplied by cosine of the angle in between those vectors, because notice theta is the angle in between vectors A and the cross product vector B and C, B cross C, then this must equal the dot product of these two vectors whose magnitudes are here. So this is literally just the dot product of the vectors B cross C and A. Now the reason why we need absolute value is because we don't want a negative volume. So that's of course just assuming everything's positive. So in reality we need the absolute values just to ensure we have a positive volume. And notice since this is a dot product is completely commutative unlike cross product was. So if we just swap these, then we get exactly that. So that I think is pretty simple to show. Right. So now this next example is kind of crazy. I want to try to use some of the properties that we saw previously, before on the previous screen. So I want to show that these three vectors A, B, and C are coplanar. Now what coplanar means is they all lie on the same plane. So in other words, the image will look nothing like this. Because notice, C and B for sure lie in the same plane. That's kind of this, what I described as being the floor. But A sticks out. If A was coplanar with B and C, then A would be flattened like this, and in fact this parallelepiped would have no volume. Its volume would be 0. So one way of showing the three vectors in 3 dimensions are coplanar is to actually show that the scalar triple product is actually 0. So we want to show that this guy, A dotted with the cross product of B and C, is equal to 0, because this would imply that the volume of the parallelepiped would have volume 0, the volume would be 0. Thus, A doesn't stick out in the 3rd dimension, but it lies on the same plane that B and C lie, so it's coplanar to those. In fact, they're all coplanar in that case. So this is basically what we want to show. Or, if you've seen this acronym before, WTS just means it's our want to show. So how do we show this? Well, we'll just actually take the cross product of B and C and then dot that with A. So let's see if we can do that. So first, let's take the cross product of B and C. So B cross C is equal to, remember that's the determinant of this vector, of this 3 by 3, ijk 2, negative 1, 4, 0, negative 9, 18. There's something I actually want to say here. There's a property we can use. So in this case, notice that C, we can actually pull out a 9 as a scalar, and we get 0, negative 1, 2. You can't do that with any of the other ones because they don't have any common factor, but 9, 0, and 18 technically have the common factor of 9, so we can do that. And we saw a property, so if we kind of call this vector, let's call it D or something like that. We saw this property that, notice this B cross C, let me actually show off this property a little bit. So B cross C is actually equal to B cross 9 times the vector D. And we saw this property that the scalar can actually be pulled out of the cross product. Perfect. So in fact, this 9 we don't really need to deal with. We can just focus on B cross D now. So that'll make the calculation a little easier. And again, I just wanted to show that with that property we saw from the previous screen. So now let's take a look at the cross product of B and D, which is the determinant of this 3 by 3, ijk B, which is 2, negative 1, 4, and then D, which is 0, negative 1, 2. And that's just our original C vector divided by 9. Good. So now if we notice, this will result in a vector. So if we cover I, right, the I row and column, take the determinant of 2 by 2, we get negative 2 minus negative 4. That's negative 2 plus 4, so it's positive 2. Do the same thing for J. We get 4 minus 0, which is 4. And then if we do the same for K, we get negative 2 minus 0, that's negative 2. Perfect. So in fact, we know that this guy here is just 9 times this, so if we scale 9 back in, we get 18, 36, negative 18. That's kind of nice you can do that. Just dealing with smaller numbers at a time instead of larger numbers, that's okay. And now we want to dot A to this. So now, separately, let's take a look at, so now let's, in fact, let me kind of separate this with a border a little bit. So now we want to take a look at A, which is 1, 4, negative 7, dotted with this guy. And in fact, really, we can pull out the 18 out of this, because that's actually just a property from dot products. So if you have your dot product of a vector and a scalar times a vector, you can scale the scalar out in front of the dot product. So notice if we pull 18 out of this, we get 18 times the vector 1, 2, negative 1, just to make things a little simpler. Perfect. So really all we need are these two vectors to be orthogonal, which I think makes sense. Now what this vector is, remember, is really just a scalar multiple of the cross product of B and C, because B and C will be some vector, and then if and that cross product vector actually will be perpendicular to B and C, of course, that we know because that's what cross product means. And if the dot product between A and that cross product vector is 0, that means they're orthogonal, so they're actually perpendicular, and we land back on the same plane that we started off with. So it's kind of nice to see that visualization come into play a little bit. But now let's get on with the dot product. So we have that 18 sticking out in the front, but Hopefully this will be 0 anyways, in which case this 18 is negligible. But let's just take a look at the dot product here. So we get 1 times 1, which is 1, plus 4 times 2, which is 8, plus negative 7 times negative 1, that is not, it's not working out actually, because we end up getting positive 7. So maybe we made a mistake somewhere. Otherwise, they're not coplanar, because we're expected to get 0. So if this was a negative 8, then that would work out just fine, but I'm not getting that for some reason. Right, so as it turns out, this is a little misleading. So I kind of did this without showing too much work. But it's important to remember the kind of signs that are associated with this. We have plus, minus, plus when it comes to the determinant rules. So, in other words, the signs of the two will stay the same, but the sign of the middle one will become negative. Which is good, otherwise this wouldn't have worked out. Because now this becomes a negative 4, in which case the multiplication for the middle part of the dot product becomes a negative 8, and that totally works out now. So now notice 1 plus 7 is 8, minus 8 is indeed our 0. It's multiplied by that 18 in front, but 18 times 0 is still 0. So what we've shown is that the volume of the parallel pipette that is determined by A, B, and C has volume 0. So the volume is 0. I kept kind of running over myself with that wording, but you know what I mean. And yeah, that implies that A, B, and C then are coplanar. And we saw the visualization that A would be perpendicular to the cross product, meaning that it's back on the plane we started off with, which is kind of an interesting way of viewing that. Alright, so finally, that's the last I wanted to discuss as far as cross products go. I really hope you enjoyed this video. Hope you found it pretty helpful. I know mainly we kind of prove things here, and I left a little bit detail out in the proofs because it would take too long otherwise. So in the next video, we'll be discussing equations of lines and planes in 3 dimensions. That's going to be pretty interesting. It will actually involve a lot of this that we've seen in this section for cross products, a little bit of dot products as well. But anyways, like always, hope you enjoyed this, and I'll see you in the next video. See you then.